I will try to address today the question, is self-organized production or even a self-organized society possible? And I'm starting off with talking about complex system because society is a complex system. If you have been interested in complex systems, and you might have heard about fractals, for example, when this field of science took off, then a lot of people were interested in fractals and also in deterministic chaos. Lorentz attractor looks like this, but there are many other attractors of deterministic chaos. You may have heard about this, and you may have heard about bifurcation diagrams of logistic maps and also other iterative maps and iterative processes or functions. And I will not go so much into this because it's maybe too much of a toy model. It's entertaining, it's interesting, mathematically deep also, but we'd like to be a little bit more close to real problems. And first of all, I would like to clarify that we need to distinguish between complex and complicated systems. This is a complicated system. A car made up of many pieces, but most of them are fixed, and there are a few controls like gas, brake, steering wheel that allows you to control all this. Right, so that's a well-controllable system. However, when many cars interact with each other on a freeway, unexpected things happen, such as those congestion patterns that nobody wants to happen, but still they occur. And in this case, when there are many parts that interact with each other, respond to each other, and unexpected things happen, we're talking about complex systems. Examples of complex systems include large supply chains, if they show interesting behavior, social, political, economic, ecological systems, also our body, by the way, it's also a complex, our brain. Financial markets, group dynamics, crowd behavior, and all this. So, more than enough to cover. So, we're not running out of subjects over here, I think. It's a daunting class of problems. We typically have a large number of interacting system elements, like individuals, companies, countries, cars. We typically have nonlinear or network interactions. We often see a rich system behavior. We typically have a dynamic rather than a static behavior, probabilistic rather than deterministic behavior, and often surprising, sometimes even paradoxical system behaviors, such as the so-called slower is faster effect. We'll come back to this later on if there's enough time. Those systems are often hardly predictable, sometimes seemingly uncontrollable, and they're challenging our common way of thinking because they behave in surprising ways. We can still learn about this, but it needs training, so that's what complexity science is about. Complex systems are everywhere around us, basically, and it's a nightmare currently for many decision makers, right? So, if you want to manage the world of today well, in all its complexity, you need to know about complex systems. A good example for the limits of predictability is the weather forecast. We know very well that it has improved over time, but there are limits of prediction. Right? You cannot say exactly what will be a day with rain in, say, 4 months' time. If we're not talking about the desert, of course, right? And that's not just a matter of lack of data, it's a matter of the system dynamics. There is a turbulent behavior over here, which is behind this. And turbulence includes that close by trajectories That means slightest changes in the initial conditions would over time lead to completely different dynamic behavior. And that's why we sometimes talk about a butterfly effect. You know, it sounds crazy to say if there's a butterfly and flaps its wings, that will change the weather in 6 weeks' time. You know, it's like maybe a little bit overblown, but it should give you this picture of slightest changes in the initial conditions given a turbulent dynamics would eventually lead to a completely different course of affairs. And here is a very nice example of how things get out of control. I hope you can see it despite the light. Oh, maybe I can switch it off. So, stop and go traffic happening here. Of course, nobody likes this to happen, but the density is so high that small variations in the speed will be amplified. That means a driver will respond with some delay to the change, and in order to compensate for the delay, he or she will have to brake a little bit harder, and that means there is an overreaction, and as a result, everyone brakes a little bit more, and in the end, cars get to stop, even though nobody wants this. And once this has happened, you can see basically the traffic jam moves backwards here, moves backwards because cars are arriving at the end of the traffic jam and are moving out in the beginning, okay? Now, many problems in the world that we haven't solved yet result from systemic instabilities, such as crowd disasters. People typically don't want to kill other people, but still, like at this Love Parade disaster in Duisburg and many other instances, people get trampled, suffocate, whatever, because the situation gets out of control. Or unstable supply chains, or in a larger system, booms and recessions. It's also about supply chains, right? Just on a worldwide scale, or nationwide scale at least. And we also find unstable social dynamics when it comes to the spreading of crime. You can see these ups and downs. Tragedies of the commons. Nobody wants to destroy this planet Earth, I hope. But still, we're doing it little by little, unintentionally. Why is this? Because even though cooperation would be favorable, you know, like use our car less, don't make so many flights, and so on, the situation is similar to the traffic flow in the circle, which was unstable, and that's why it broke down. Over here, cooperation breaks down because it's unstable, and that creates the tragedies of the commons. Now, the question that I'll ask later is, can we stabilize cooperation, and how? Conflict, same thing, you know. In many cases, it's not intended, but it happens. And just think of divorces that was not planned when you got married, or you know. But somehow, little by little, things get out of control, and similar things can happen between countries. Revolutions, when the GDP per capita goes beyond a certain threshold, apparently autocratic systems are not working well anymore, or destabilizing, because if you want to be entrepreneurial, which raises GDP per capita, you need to have entrepreneurial freedoms. And so, yeah, instabilities again, and it's interesting to look at this experimental example where we have many mouse traps with table tennis balls on top of them. You can see it starts with one little table tennis ball falling down, and then it messes up the entire system. This is a nice experiment for a rainy day, by the way. Yeah, be careful with your finger. We did that with 400 table tennis balls in Berlin, by the way, recently. And even though that looks like a entertaining thing, this chain reaction, we find similar effects in reality, such as the financial crisis, right? Lehman Brothers was the single table tennis ball in a sense, it triggered off the bankruptcy of hundreds of banks, and that created losses of hundreds of billions of dollars. The systems that we rely on shouldn't behave this way, of course, but it shows you, I think, that these kind of cascading effects are happening, and they can be very destructive if systems are not well designed. Now the question is, can big data fix those complexity issues? Of course, I'm a fan of using data as a computational social scientist. And now there's more and more data, because basically everything we do produces data traces, right? If you Google 700,000 times, this happens in just a minute. If you send a Facebook post, that happens also, now wait a moment, 500,000 times. If you go shopping, if you move around, all of that creates data traces, and that of course has also fantastic implications economically in principle. At least the most valuable companies right now are basically big IT companies. They've overtaken those oil companies, and that's why people say data is the new oil. And so the idea is, the more data you have, the more knowledge you have. Knowledge is power. You can see what's wrong. You can see where the system is broken and then fix it, right? And Chris Anderson basically suggested if we just had enough data, we would have such a detailed picture that the data would speak for itself, and we would not need science anymore. No theory, no scientists, bye-bye. And interestingly enough, there were not many scientists who say, wait a minute, who do you think you are, and can we be sure that you're right, because he was not. It turns out there's much more data than we can process, and that's why we need scientists to decide what pieces of data to process and how, right? So you can have a job also in the future. But in the beginning, it was not so clear. I mean, many politicians and also business people believe that narrative, that storyline, that just collect as much data as you can and it will tell you everything. You don't need to have smart people anymore. You just need to have a huge supercomputer and a huge database. And what they didn't realize that the more data you have, the more patterns are in the data just by coincidence, right? Like, look into the skies and you'll see patterns. Some people give names to it, but the scientists would say those patterns don't have a meaning. You just think they are there, but this is just what you see. This is called spurious correlation, a typical thing number of serial killers as a function of chocolate consumption. It looks like, oh, there's maybe a linear relationship. Oh, maybe we're living very dangerous here in Switzerland, but no, because here's the reason. There is no causality here. It just happens to look this way. Yes?
Where is Switzerland in this?
Well, up there, I guess.
I mean, chocolate consumption is definitely high, but what about number of serial killers?
Good question. Yeah. so far, I think we're pretty safe in Switzerland. But you know, the point is these kind of things don't just happen. Stupid people who haven't learned to handle data. I mean, we would think Google knows how to handle data, right? And they came up with Google Flu Trends. And it was one of those examples for big data successes in the beginning when we had this big data boom. And then eventually it didn't work anymore. By the way, because they're influencing what you're searching for. They didn't always do that. So they're influencing the measurement in a sense, right? And now they took it off. They don't offer that service anymore. So it's not the success story anymore that they thought it would be. Now, people saying, okay, maybe we need to have something more intelligent. What about artificial intelligence? And I also like it, and don't get me wrong. And maybe even super intelligence, you know, something smarter than us. Whatever. So, I mean, certainly artificial intelligence is quickly progressing. Some people think we'll soon have super intelligent systems. Other people say we'll take 40 years, 100 years. Some people say, oh, the military probably has it already. Whatever. We can certainly say that computers are playing chess better than humans already since a long time. They might be better drivers. They seem to be better in answering questions, at least those questions that already have an answer. They are even capable of beating the world champion in Go. That's a very complex, I would almost say, not just complicated, but complex strategic game that people thought, oh, it would take decades for AI systems to beat the world champion in Go. But that happened already back in 2016. And in the meantime, they have AlphaZero at Google, which learns by itself how to win. It just plays against each other, you know, and tries many different moves, and eventually it learns what works and what doesn't work. It learns to play chess within 4 hours, and then it will beat you maybe already after 2 hours. It's like just amazing. And robots will certainly become more and more capable and sophisticated. They can learn from each other very quickly, right? There is a robot cloud. Some companies at least build such a thing. So when one robot learns how to do a certain thing, this kind of knowledge can be used by another robot in a different country or continent, basically within just a few split seconds, right? Well, we go to school for 12, 13 years, and then we study for 5 years, 6, 7, whatever, do a PhD for 3, 4, 5 years, and then we specialize, you know, so that's the situation. Like at the moment, it's kind of clear that we also need a little bit of technological support in order to get immediate access to new knowledge and support by digital systems, basically to apply what other people have learned in the world just in the next second, right? I'm talking here about mixed reality glasses and stuff like this, which basically instructs you to do complicated stuff without having to learn that for a long time. Not necessarily neurochips, but people are working on this too. So, and then some people were asking, could we maybe run society like a giant machine? Yeah? And just imagine everything that can move would be treated like a black box that can learn. So there's machine learning algorithm, you feed it with data about that thing, be it a company, be it a person, be it a car, whatever, and that black box learns to behave like that person, car, politician, company, whatever. People are trying to do that. It's not publicly known so much how well that works, but it's being tried. That's what I can tell you. And Google is not just working on operating systems for computers and for smartphones, but they're also trying to reinvent the world, society and how it works. And they've said that publicly, so it's not something secret or anything. And they have their places where they're basically trying this out, and some people think, oh, that's fantastic, and other people think, oh my god, that's a nightmare. So far it's not working so well, right? So if you look at the leading countries in terms of quality of life, then interestingly enough, there's no city that comes from a leading IT nation. And why is this? Why doesn't it work so well? Because the city is not just a giant supply chain. It's also not just big entertainment park, right? Like some people saw, okay, there's the entertainment parks and there's kind of tens of thousands of people, or even hundreds, I don't know exactly, in a day. So basically that's like a city, and those entertainment parks are perfectly organized. And why don't we run cities like this? Well, the reason is because cities are more than an entertainment park. The cities are places where we experiment and learn and fall in love and do projects with people and are creative and innovative and all these kind of things. We don't just want to consume pre-manufactured stuff. We want to do something, right? And so that's basically something else. This is about participation. And there's also an official report about this. So cities were on board and big tech companies were on board and Homeland Security and all this from all over the world. Now, why isn't it working anyway so well? Because many complex, in particular social complex systems, are scale-free. That means we have a power law distribution of the number of friends. Some people have a hell lot of friends and other people just have one best friend. And there's a long tail distribution of this, and if you have these kind of systems, then your mean value or your variance may not be defined even. So that's kind of an ill-posed problem. And in these kind of systems, your learning algorithms may not converge. Could be just the opposite. So usually, learning means you have an iterative process that improves, and so you have a convergence to the true state of affairs. But you could have a different thing where you don't converge against this true state of affairs. We could even have a divergence. And Google typically what they did in the past is, okay, let's don't just do a million or a billion or infinite many iterations as a mathematician would do, And they say, oh, let's stop the process after 3 iterations, to save energy and computational time and so on. And the question, how well does it work? Does it work? When does it work? And these questions are not really well answered so far. That's also why we need scientists. And for such reasons, for example, bias is a huge problem. Some people say even bigger than killer robots, right? Because those are not being used yet, I hope. But machine bias is real, and it hits people, right? Like people of color, foreigners, women. We don't want people to be discriminated gains. But they do it, like people do it too sometimes. But the idea that AI systems wouldn't have all the weaknesses that people have, that idea was wrong. In fact, it turned out that these AI systems that you feed with streams of data, that they can be manipulated too. Right? And now, one of the biggest problems right now with the internet is fake news and hate speech and all that stuff, and so the idea is, okay, let's filter it out. Some people speak of censorship, and I think we have to be worried about these kind of things, but the worst thing is, it doesn't work. So they try to apply powerful filtering algorithms, AI, right? Facebook is one of the leading AI companies, and they had to give up on it. So basically one day Mark Zuckerberg said, we're going to link to Wikipedia. That was a big surprise to Wikipedia because they didn't even tell them before. And that means they admitted in a sense that collective intelligence, because that's the principle on which Wikipedia is based, is superior to artificial intelligence, no matter how big. So, your smartness still matters, but you have to link it. Okay, so let's come to computational social science. So this is basically bringing all of this together, right? Social science with data science, with computer science, with learning algorithms and all these kind of things. So it's an interdisciplinary research field. So people come from different areas and make contributions. And here we see the reason why actually Google Trends doesn't work so well, because we don't have this diffusive mechanism spreading diseases as we had it at the time of the Black Death, by the way. More or less, the Black Death spread like a diffusive process. But now we have this instead. Nice animation by Dirk, by the way. So people take planes, and so the disease jumps to other places, and so that messes up basically the process, makes it difficult to understand what's going on. That's why you have these widely scattered data clouds. Very frustrating for a scientist. You look for correlations. Space-time correlations offer new disease cases come up when you look at the globe. You have a sophisticated data tool that feeds it all in. Think that doesn't make any sense. And it's because of this. You're taking planes and spreading diseases, even if you don't know it, But you can then use that information about passenger volumes going from A to B and B to C and so on in order to define a new kind of effective distance. And if you do that, the spreading process becomes again a diffusive process in that effective distance, and you can determine the most likely place of origin of the disease and the most likely next cities hit by the flu. And in this way you can prepare, you can basically put doctors and nurses and medicine in those places in order to help contain or at least better deal with diseases. So look also, now it looks linear in this other presentation. So that doesn't happen just by your AI going through the data. You need to think about the process which is behind this, and that will tell you how to look at the data and how to combine different kinds of data sets in such a way that suddenly it makes sense. And that's why we don't talk about big data analytics so much here, but about data science, right? So that's why we need ETH. and you smart students. But in complex systems, we need, I believe, a new approach. Certainly with the availability of big data, we could go from a situation where we didn't have enough data to take good decisions into a regime of evidence-based decision making. But look over here, while processing power doubles every about 18 months, data volume doubles even more quickly. Currently, every 12 months. That means in one single year, we are producing as much data as in all the years of human history before. It's unimaginable. In the future, data is expected to double every 12 hours. Amazing. So, all the computer power will not be able to catch up. So the amount of data we cannot process is increasing in percentage. That means there's dark data, and this is why you're still needed in the future. Science is needed to decide how to look at data. I just gave you this. Yeah. And on the other hand, we network systems, and this makes systemic complexity increase in a combinatorial way, because networking goes combinatorial, and that explodes even faster than exponential. For that reason, even data volume most likely cannot catch up, and we need to have a different control approach, distributed control. Yes?
Why are we continuing to collect all this data if there is no way we are ever going to analyze it?
Well, the idea is, if you have more data, you can still improve, right? At least that has been driving the process. The other thing is, data is like coffee, after nobody is interested in cold coffee, nobody is interested in old data, so that's why we produce new data, right? So, the world is networked. But you can very well imagine, like, if you do something in here, it will have an effect on those people, companies, and institutions that are linked to that person, right? And so the more the world is networked, the more it happens that not intended outcomes occur, but there will be side effects that in many cases have not been anticipated. There would be feedback effects, and or there would be cascading effects. And that's why I conclude that planning the world in a top-down way and then regulating it is not going to work well, but we should think about a different paradigm of designing systems in such a way that reasonable decisions would be supported, but we would still have some freedoms of choice, relevant choices. Now, interestingly enough, large complex systems can self-organize in many cases and create outcomes that are favorable. Pedestrians, for example, here is a model, how we model pedestrians, an equation of motion for pedestrian alpha plus an acceleration equation. And we assume that acceleration equation is made up by different terms, like a driving force, an interaction with boundaries, and so on. And then you can simulate things and actually get phenomena that are known from reality, such as lane formation. That means after a short time, you can see that the oppositely moving pedestrians are segregating into lanes of uniform walking direction. So opposite streams separate from each other. That produces an efficient self-organization. There's no law, no policeman, no traffic sign, nobody telling people to do that. You do it too. Probably you didn't know. It just happens by self-organization, like magic. There are other examples, such as bottlenecks. So what happens in bottlenecks? Well, we'll find oscillatory flows. The red ones are hard to see, but at least the other ones. So there's a door, and people are pushing from both sides, and basically there's a discharge of one side. On the other side, there are more and more people accumulating and waiting, pushing, and so there's a pressure effect that creates these oscillating flows. And it looks like there's a traffic light, but there's not. Again, based on self-organization. And here, again, is an example that we call stripe formation. Pretty amazing. So two large streams of people crossing each other. And it will be possible for you to cross the other flow without even stopping. By walking forward with the stripe that forms and walking sidewards within the stripe. So, again, that can happen by self-organization. Even if you couldn't figure that out theoretically, I'm not sure I would have found the solution, but these kind of things happen. I find that very amazing. So why don't we organize the world in such a way, and use these tricks? In effect, pedestrian facilities can be largely improved. These are the classical design elements. These are corridors, bottlenecks, intersections, all wrongly designed. So if you cut away those corners, it's better. Makes sense, right? So funnel-shaped design, less obstruction. But that tells you, hey, wait a minute, less is more. If I take away space, it can be better for the system. Unexpected. So what happens if we put some obstacles in here? It turns out to stabilize the flows and to help separate the opposite walking directions. And also for intersections, we can have innovative solutions that, in this case, would create a counterclockwise flow rather than chaos in the intersection area. So, interesting stuff. Once you learn to think in self-organization, behaviors, pattern formation, collective behavior, there are new solutions. Let's take traffic. We're suffering from congestion basically every day. Here's a freeway with an on-ramp. Some cars want to get on the freeway. You can see this is the density in the course of the freeway. This is the course of time. Downstream of the on-ramp, there are more vehicles. That means the density goes up a little bit. But there is a seemingly stable flow. Now we reduce for some time the density. And we would say, oh, that's good, because it would improve the traffic flow. Well, what happens instead is this little dip over here, it will deform over time as it travels forward. It passes already this on-ramp, then eventually the amplitude gets so big that this thing turns around. We call that the Boomerang Effect. So in the beginning, we have a cluster of cars moving forward. Later on, we have that traffic jam effect traveling backwards, as I explained to you before. Then we get again to the position of that on-ramp and traffic flow breaks down. The same freeway has less capacity at that point in time. Capacity is a dynamical effect. It's not just given by the engineers, it's given by the cars' interactions. And then you have this oscillatory traffic flows. All of that happens just with a very reasonably simple equation. No parameter variations. You do this. You don't even know about it. And now you know it. Interesting, isn't it? And there are so many different complicated patterns of traffic jams, and you would think, oh my God, can we ever understand it? But at that time it was already too late, because I was a traffic scientist at that time. We had published about traffic equations, and then data came in and told us what really happened, and we said, ah, and had we known before, but it turns out we got to understand all this. With relatively simple models such as this intelligent driver model, right, there is again equation of motion, acceleration equation, which depends on the distance, relative velocity, velocity of the car. It's made in such a way that usually accidents wouldn't happen. And depending on the inflow, for example, through the on-ramp, there would be different traffic patterns resulting. A whole slew of different congestion patterns. Who would have expected this? Amazing. This is a simulation. That's what we later found in the data, so it's all there. And there are predictions about when, what kind of congestion patterns might happen. It also depends on the size of the perturbation. So history dependence, initial conditions matter, multi-stability for those who know about this kind of thing, kind of interesting complexity that can be boiled down in reasonably well understandable diagrams, so-called phase diagrams. And the best thing is it works. So if you look at data, it fits the pattern predicted by those traffic models. We can even predict the extension of congestion patterns and the delay times. The only thing we cannot predict is when congestion sets in. And this is because it might depend on a small perturbation. Think of that table tennis ball. It could be one truck overtaking another truck. And when that exactly happens, it's hard to say. But that could be the reason, right? And then we can calculate how many minutes or hours you'll have to stand in the traffic jam. Yeah. So now we have an analytical theory of traffic flow. And the question is, can we use that understanding to overcome congestion, at least to some extent? And the answer is yes. So just consider that cars are getting smarter and smarter, so they have all sorts of cameras and sensors and have all sorts of data, so they have perception in a sense. They can, depending on their technology, communicate with other vehicles. They might be able to determine the traffic state themselves, so they have cognition. Maybe they determine the traffic state together, like through collective intelligence, because your local measurement may not be good enough. And then you want to take a decision how to change your behavior. And so we have worked on putting different kinds of data together to produce a good picture of what's happening, and then we figured out how to change the driving behavior of the car in such a way that it would not only increase comfort of driving, but also it would create a collective behavior that is more favorable than a traffic jam. So we figured out how to dissolve such a traffic jam. Even if not all cars are equipped with that self-driving equipment, so-called adaptive cruise control, but maybe just 20%, we can largely reduce the traffic jam. So some improved driving introduced can benefit everyone. Right? And here is a visualization of how it would work. So first of all, I'm showing you that we can reproduce stop-and-go traffic that we find in reality. So we understand the process, we can re-engineer it in a computer. And then eventually we get so much annoyed that we're leaving the car. We continue with a helicopter instead, and now we can see, oh, the reason for the traffic jam is those cars that want to slip into the freeway and produce small perturbations in the traffic flow, and those perturbations are amplified and that produces stop-and-go traffic. And now we will turn on, in a second, the adaptive cruise control, where cars are measuring distances and relative velocities with, say, a radar sensor, and then drive automatically. And you can see that now the traffic jam is dissolved. Even though we haven't reduced the inflow, we just changed the interaction between the cars. We call that mechanism design. Before self-organization produced traffic jams, now it dissolves traffic jams. And what's the trick? Well, we need to have real-time measurement, real-time data, real-time feedback to change the interactions in a favorable way. And in this way, we have stabilized the traffic flow and increased the capacity of the freeway back to its maximum capacity. Yes?
Well, the infrastructure was staying the same, right? You could also change the intersection.
Oh, absolutely. You can do a lot of things, but the interesting thing is here you don't need to add additional infrastructure. So it's good for the environment.
No, you still have to add additional infrastructure, you just have to do it with cars.
It's a different kind of infrastructure, but wouldn't have to take away trees and that kind of...
Yeah, but you will have to make new sensors for every car. I wouldn't be so sure what is better for environment.
Well, certainly this is what they are for, to figure out what are kind of the environmental impacts of those different solutions. Yeah?
It was only 10% of the cars.
Yeah.
Unless you showed in the last slide.
I showed that we don't need to equip all the cars with that technology, which is, by the way, also important from the point of view of a car company that wants to introduce that technology and needs to have a critical mass of cars equipped with that technology to have the collective effect, right? So a lot of good technologies could never be deployed because everyone would have to use it at the same time, more or less. Otherwise, you pay a high price for a new piece of technology and it doesn't work because all others would have to have that technology too. So there's interesting stuff, and I accept your argument, but it needs people to sit down and basically figure out what are the environmental effects. And then we do what the data say. Yeah. Now, urban traffic is another problem, right? And it could actually also work in a self-organized way. This is a very amazing example that I really love to see. Highly diverse traffic flow and no traffic lights, no policemen, but it works. And how is this possible? Any ideas? Well, it's the design. Here we have unidirectional traffic flow in the back into the opposite direction. And there is a small buffer in between that allows everyone to adjust the speed in such a way that you can just cross the road when there is a gap for you. It's all about adjustment, flexible adaptation, which is supported by this design. And we have been inspired by those oscillatory flows that were self-organized, and so, oh, couldn't we transfer this principle also to intersections? Because intersections are, in a sense, bottlenecks, but just for more flow directions. Could we define a pressure principle that would create self-organized waves that would define traffic light operation? So the traffic flows would control the traffic lights rather than the other way around, in a bottom-up way. And so the question is, how well would that work? I mean, most people would say the best thing you can have is a traffic control center, right? This is what we're looking at over here. Traffic control center is trying to collect as much data as possible from all over the city, and then it's trying to figure out an optimal control schedule. The problem is it's an NP-hard optimization problem. There are so many parameters you can vary, and each parameter variation is coupled with thousands of other potential parameter variations at other intersections. So there's a huge solution space, and you cannot go through all those possible solutions in real time. And then you basically have to simplify the problem, and people say, okay, then why don't we go for a periodic operation of the intersections and then synchronize the different intersections, problem solved. But while you're doing this, you're throwing away all non-periodic solutions. And there's a lot of non-periodic solutions that are better than any periodic solutions. Even if every so and then you change your periodic solution to another periodic solution. So what usually is being done is you come up with an optimal plan for a typical traffic flow situation that has been measured before. And so you have an optimal plan for Monday morning, 11 o'clock, and for Tuesday afternoon at 4 o'clock, and Friday kind of rush hour traffic after work, and then Madonna is having her concert and all this kind of. So for these different situations, you have optimal plans for typical traffic flows. But then it turns out there is no typical traffic flow. Never, ever. The variability is as big as the mean value. So you have an optimal solution for a situation that never occurs. Then you can try to adapt green times a little bit in response to measurements, and that's what people do, but still you have a variation of periodic service schemes. And I said, let's see what happens if we had local control. Traffic flows would control the traffic lights. And that's kind of homo economicus approach. Like each intersection is treated like a homo economicus. Every intersection wants to do strictly the optimal thing for that intersection. And then the question is, what happens there? You'd think still the centralized control should be better. And then finally there is a third approach where we do the same thing, but if there's a long queue, we would first clear the queue before we go back to travel time minimization. So we would think, oh, this is is not so egoistic as this approach, the homo economicus, so that should work better than this, and this should be working better than that. So that's what we expect. And then it turns out, no, it's not at all like this. No. So as you increase the utilization of capacity of the intersection, for the top-down regulation you get the red line. So the more traffic, the more cars are queued and waiting. Makes a lot of sense. Now, if you go to the homo economicus based approach, you see, oh, that's actually much better if there's little traffic flow because it's adaptive to the situation. But then suddenly, queue length explodes and the thing doesn't work anymore. So basically we can say, here, Adam Smith's invisible hand works nicely over here, because you don't have to wait until the cycle comes back to you. But it really fails over here, right? And now the traffic light control center says, see, and that's why you have us, and pay millions for the traffic control center. But then comes the third solution, which is this other regarding one. That means selfishness, but with some eye on your neighbor. So you're kind of behaving nicely to your neighbors. Take it into account. And that works all the way better than the centralized traffic light control. So we can make the invisible hand work. And then the question is now, does it just work for a theoretical scenario? Or does it also work for a traffic system as complex as this? This is Dresden. And they had terrible congestion in the center. And then they made a competitive call for a software that would fix the problem. That is the area which they, in the end, were still not totally satisfied with. What they bought was expensively. Traffic light control that produces green waves, and even adaptive green waves, given the measurements of the incoming cars. But what they couldn't do is at the same time prioritize public transport, which they wanted to do. So many different tram lines and bus lines, you know. So if you would prioritize for those, you would have to interrupt the green wave, and that basically messes up the green wave, and you have a monster traffic jam within minutes. And that was very frustrating to them. And we came up with something that was more adaptive to public transportation. So you can see this is the green waves that they produce with their state-of-the-art software. This is what our system produced. So not so periodic, not so repetitive, just responding to the situation. And the question is, how well does it work? And then it turns out that it's, of course, a large improvement for public transportation because we did some prioritization, but not at the cost of cars. They even had a small gain. And it was also good for pedestrians and cyclists and for the environment too. Because we engaged in a flexible and adaptive approach that would spread coordination among intersections in a self-organized way. Self-organized coordination. So and now the question is, can we also apply that to logistics and supply chains? Right? And there we have some correspondence to road networks. So for example, road sections correspond to buffers, travel delay time to cycle time, congestion queues to full buffers, junctions to processing units, different origin destination, relationships to different product flows, conflicting flows, traffic light scheduling corresponding to production scheduling, green waves to maybe convict strategy, accidents, machine breakdowns. So it's not all identical, but at least there's some degree of similarity. So the question is, yeah, could we improve that too? And so we have been looking into models of supply chains. First, linear supply chains. We assume that companies would adjust their production rate to demand, but with some delay. So it takes time to adjust, right? And so if you have many companies in the raw that are delivering to each other to produce a product in the end, then you could get a bullwhip effect, and it's a well-known effect. Yeah, also it appears in this beer game. You can play that with managers even. They would also fail to produce a stable supply chain in that setting. Yeah? So, we can understand these things with models. And here's one of the problems that we've been looking into when I was working as a professor at TU Dresden. And Dresden is kind of the Silicon Valley of Germany, so they have Infineon Technologies. It had at the time, I think it has a different name now. And they were producing silicon wafers, you know, in other words, computer chips, memory chips, these kind of things. And so what happens is you have silicon, you basically apply high frequency light patterns to those silicon wafers that structures what you want to get, and then you have to put that into different kind of chemicals in order to etch out structures, and it has to be washed in between in water. There's different chemicals that are not compatible with each other, and there's a minimum and a maximum passing time in the chemicals. If you stay shorter or longer, you will have poor quality. You have to throw this thing away. And you want to have as many processes in parallel as possible in order to have the maximum throughput, right? Now, the first thing they said, we don't reach the throughput that the producer promised us. Even with the help of the producers, we don't get there, and we have very bad predictions, so we made many measurements of throughputs depending on the parameters with which we were running the process. So many different measurement points, and then we want to interpolate between those points where we had measurements and predict what will happen for another parameter set where we didn't make a measurement yet, and predict the measurement. And it turns out very bad predictability. So also that didn't help. And so this is how it works. So you have this dripper over there, so it takes those silicon wafers and then puts them into the chemicals, and water, chemical, next thing, and so on and so on and so on. So you can imagine how, oops, it works. So, and we managed to increase throughput by more than 30%. How did we do that? That's the slower is faster effect. And what they were trying is, to get more throughput, that's reduce the passing time, so things go more quickly, and now we can rush through many more silicon wafers. The problem is you just have one handler or gripper, and this thing is busy, and if there are two processes asking to be removed from the chemicals at the same time, you can just handle one, and the other one will have to wait, and by the time you can handle it, it will be poor quality, right? So we said, okay, slow it down. So you can coordinate this process, and this is what we did. So we went from here to there, so longer processing times, as you can see over here, and that did the job. Then somebody else called us and said, we read about your pedestrian work and we were impressed, and we have a problem, and this is a container harbor. And they say, we have so many containers, and our business is booming, but the problem is our automatic guided vehicles is almost a little bit like trains, automatically controlled. They can't handle it all. And I said, slow it down. Because if you have those automatic guided vehicles go at a large speed, they would need to have more safety distance. And that means there is a higher chance that they would block each other. So smaller speed means less safety distance, less blockage, and of course you have more run time or moving time, but less waiting time, and altogether you will be faster. Yes, and then we said, okay, what about supply networks? And we extended those equations that I mentioned before. So you can see here is an input-output matrix, as we say about it. So it means what kind of materials go in, what kind of stuff goes out. And then it turns out those equations that I just showed you, they have different kinds of so-called regimes where the system can behave differently. So we can have, for example, damped oscillations. I mean, when your system is away from equilibrium, it will go into equilibrium as economists usually assume, right? It could also be over-damped behavior, but also we could have damped oscillations or even growing oscillations. And then we say, okay, let's plug in an input-output matrix of world trade. So you have industrial chemicals, agriculture, wood products, construction, mining, petroleum, electricity, all those interdependencies that have their internal logic, but then you have numbers for this. And you plug it in and you get basically this. And there you have it, booms and recessions. And not periodic ones, as most textbook examples predict, but non-periodic booms and recessions as we actually observe them, right? Next question, could we maybe reduce those oscillations? And the answer is yes. How do we do that? Well, we've been looking into different kinds of organizations of those supply chains, right? Like linear supply chains, and here this kind of hierarchical chain that splits up, and then you have something like a ladder. And it turns out this produces really huge oscillations, and that one also has quite substantial oscillations, but this one, the ladder, dampens out oscillations almost completely. Wow, yeah, why don't we do this? And in fact, it turns out Intel is doing it. It's not so clear whether they had a theoretical reason for doing this or whether over time it just happened to grow like this because it worked. But in any case, you can see that this ladder kind of design is working. Next thing happened is, oh, Professor Helbing, we've read about your pedestrian work in the newspaper. I think that was in a British newspaper because it was a British company, packaging plant. And I said, we have a problem. Our corrugator, which is the machine that produces, how to say, packaging carton, how to say, coverage. This machine tends to break down. So whenever it's repaired and running, we run it as quickly as possible to get stuff done. And I said, that sounds like a faster is slower effect. Because really what happened is, because they were running it so fast, the problem was, as it turned out, not the corrugator over here, but the buffer that had to take all that stuff in and store it. And it ran full. I mean, full means in a logistic system, you have a 60–70% buffer filling is almost like 100% in your imagination, because it takes so much time to get things out and in, so you have to get something which is over there, you have to remove all the other stuff before, in order to get there, and then put the stuff again. So that means don't go beyond 60–70% in many of those logistic buffering systems, or you need a very intelligent solution, right? Okay, so the problem was not the corrugator, but the buffer. And in fact, what happened is yeah, we had traffic jams. And so a bottleneck developed, and that produced traffic jams and missing quantities downstream. And as somebody who did traffic science before, I do understand how it all belongs together, all these interdependencies. And so we were starting to simulate that stuff in a computer and built a simulator for production plants. And basically we had representations of those different machines, and they could be put together in different ways. And so you can see over here there's an abstraction going on, represented through a network of sinks and sources and links. And then we have an agent-based simulator, did at that time, that was basically simulating the processes in that factory. You could also take out this and put it somewhere else, and this way do kind of evolutionary optimization and see how it performed, right? But now the interesting thing is, it was hardly possible at the time when we came up with the idea, but now we have the technology for it with the Internet of Things and RFID chip and even more smart devices, right? So the idea was the products would be able to talk to the machines and tell the machines, do this with me to basically finish the product or improve it, progress it, whatever had to be done with it. The other thing is the products could talk to each other. So for example, this package could say, look, I have to be delivered very soon, so please let me overtake. And the other product said, okay, I have a little bit of time, so I can let you pass. So that is kind of a smart factory, right? When those objects can start to talk to each other. And so basically also those objects can respond smartly to the situation. For example, rather than taking the shortest route, it might sense to take some detours sometimes in order to avoid traffic jams, right? And so what you'd like to have is a layout and also an operation that would support cooperative production, or could even say social production. And here's a nice example of a colleague, Kai Foreman's. So you can see there's a conveyor belt. In the beginning, the products just take the shortest path, but eventually we make the conveyor belt busier and busier and busier, so they would be in each other's way. So eventually they learn to move in a counterclockwise way. So, smart collective behavior that emerged from those interactions. You just need to have a framework that allows it to happen. Right? So, yeah, then the question is, could we come up with a self-organizing, sustainable economy? It was always the dream, at least for 300 years, to have an economy that works like a beehive or a flock of birds. Now, planes in Kloten at the airport, you couldn't do such a thing. You would never take a plane if the airport was as busy as this flock of birds, right? But now with the Internet of Things, it's doable. And so we can say, 300 years after Adam Smith's invisible hand concept, we can now make the invisible hand work. With real-time data, real-time feedback. Even your smartphone has, in a sense, the Internet of Things in a pocket. You could basically connect your smartphones together to create a collective measurement device. Yeah? You can equip objects with sensors, and by doing this, basically equip them with senses, right? You can also add some artificial intelligence. So I don't know how a table will be in the future, but it would probably also have sensors and motors and maybe fold itself. You have that already? No, it might fold itself or just put itself in a different place depending on how you want to use the room. Yeah, and here's an idea. So what are we doing about the sustainability problem? 50 tons of stuff being thrown away by people in industrial countries today. And so materials are short in other countries. So if we would learn to recycle all this, it would be enough for everyone on this planet. And so the idea is, yes, we can now use the Internet of Things to measure all the side effects, so-called externalities, noise, stress, CO2, dirt, garbage of all kinds, and also positive things, like health, education, new jobs, reuse of resources, and so on. And so we'd like to increase positive externalities, reduce negative ones, and compensate people in a fair way. And in such a way we would, like with the traffic flow on the freeway, we would have real-time feedbacks that would improve the flow. In this case, we would want to have a circular flow, recycling, right? A circular economy. And for this, we would need to have a multi-dimensional incentive and feedback system, for all the different resources, different kinds of plastic, glass, and steel, and aluminium, and so on. We'd have different currencies, in a sense, like different bank accounts, and so we would have different feedback loops, and this would be able to manage complex systems. So we have had the summer school on bringing blockchain technology together with the Internet of Things. I believe in spring we'll have another school like this, so if you're interested, it was really amazing to me. And so the idea is to introduce new forces into our economic system that would cause attraction and repulsion effects in such a way that resources would flow to the places where they should go, and they would close the circles, produce a circular economy. We could have smart waste that knows what kind of materials are in there and what needs to be done with it. It could tell us and could tell machines what to do with it. All of these things would be possible, and of course sharing economy would be part of our circular economy, right? So the idea is basically to have in the future a system where we have a circular flow, like the transport as a service, Google cars, for example. They would ideally never stop, basically pick you up, bring you to work or to some other place, pick up the next person, and so on, and would be on the way all the time. So we would need less garages and more parking space and less cars and all these kind of things. We would do the same thing with all the logistic flows and money flows and so on. It would be just there when you need it, and then it would go somewhere else, where it's supposed to be.